Okay. Okay, so good afternoon all and welcome to this particular Gyan course. This is going to be conducted in online mode. So the guest faculty is Professor Amseni Sadiki from TU Darmstadt, and there will be few lectures which would be taken by me, and each day we'll have 2 sessions. So in our timing it would be 3 o'clock to 5 o'clock, session 1, then there could be session 2 follow up at 7 o'clock to 9 o'clock. And just to initiate the process, so I have invited our department chair, Professor Khusari, who is alongside me, and also Professor Sadiki is there. So I would request Professor Khusari to say a few words so that we can start this proceeding.
Welcome everybody to this Gyan course organized by Professor Day of the Department of Aerospace Engineering. And this is a very topical topic for the discussion at the present day, which is, I see, is the multi-phase combustion theory and modeling. And I think this course is going to discuss about atomization as well as turbulent combustion. And incidentally, I have done my PhD in atomization, so I know the importance of this topic. And I have been working myself all my life on the atomization and liquid combustion. And I know the difficulties that we face both experimentally and numerically. I hope they'll be able to address some of the issues. But still, this is a very vast field. And this will be a good effort to try to address some of the issues that is faced in this topic. And again, I like to welcome Professor Sadiki from the TU Darmstadt for participating in this event. And maybe the participants will be enriched in their knowledge by attending this course. With this, I will not take much time, so I request Dr. Day to continue with the session. Thank you.
Okay, thanks, Professor Khusari. Yes, again, we formally, on my personal behalf and on the behalf of the department and IITK, we'd welcome Professor Sadiki for this particular course. So as I said, this is going to be conducted in online mode and in a webinar fashion. So participants are requested, they can, type their question answer session in the Q&A chat box, so that towards the end of each session, so whoever is the faculty or instructor, he will take it up, and we have also some coordinators who will keep on checking those question answer things. So that's how we are going to operate this one. Okay, so these are tentative schedule of this. It's already there also in the website. So there could be maybe slight small change in the topics. Essentially topics in the sense reshuffling of the topics as it's kind of provided as a fashion, but otherwise all these topics would be covered in the next 5 days. So we'll have it over in that fashion. So that's pretty much from my side. Yeah. So now all these lectures are recorded, and as per the requirement, probably at the last day we might have a small objective type exam as well, which is and these lectures all are going to be recorded, and these are going to be also uploaded in the IIT Kharagpur Gyan portal. So that's so you don't need to worry about that. Okay. So with that, I would, now I think I would hand it over to Professor Sadiki. So you may share your screen, and now it's up to you. So.
Yeah, many thanks for inviting me, and for this time we will share together with all people. So let me bring my transparencies, my slide on the screen. I think you can see it.
Yes, it's visible.
I'll put it in presentation mode. And I have tried to not present our university. I think it is well known, the Technische University of Darmstadt. And if it is wished, then I can present it later. So we will focus on the spray combustion school. And this school will focus on different topics we have to share together. And I think I will put at the end also some issues concerning multi-phase flow combustion and not only the spray combustion. So let me start a little bit with this movie here. So we spray, and from this spray we see that it is a really complex process from atomization and the spray formation, dispersion, evaporation, and also at the end, I have not shown it here. So we have also combustion and also some radiation processes. So this kind of phenomena can be found in different applications. We see here, for example, the biomass application. We see also the pollutant formation in the atmosphere and from buildings. We see here also in the medicine, in the metal processing. We see also here in engine propulsion, in aerospace for steam generation and energy generation, like here for stationary gas turbine and aircraft. And we see here also in transportation on road, we see in ship, and we see also some other applications here, for example, for cooling processes. So we can find it also in IC engine and also in some kind of after treatment, exhaust after treatment. So it is very huge, and we can see also some application in chemical engineering, also in some other processes related to rheology and so on, but we will try to focus here on energy production. So here is a small slide, it is a small short movie to show only how we did it. For example, in IC engine, so it is a part of movie to show the motion of and also the intake part and exhaust part. And we see also that this is very complex, and that is what we have to study in these lectures. So, focusing on energy production, as I said, we see that the resources of energy sources is very limited, and these lead to some problem in the world. You know, there are some geopolitical restrictions, and also transforming these primary energy resources to energy bring also some local and global environmental impact. which is related to pollution. So this led to innovations of technologies, and this is which bring these this field in great progress. So we can see here that the global energy consumption is very high, and if these resources are really limited, then we can see that there is really a problem with this, and that is why also at the moment there is some development related to renewable energy. So now there is almost 12.6% of renewable energy which is consumed. But the most part, oil, coal, and natural gas, as produced naturally, are transformed by using combustion, and that is what we will show in a few minutes. So that is a country, and we see that India is also a big consumer of energy, with in 2019 and then 2020. So there is a great augmentation of consumption in of energy, and this is the energy produced by fuels. And if we put it from 1900 to 2020, so we see that the ratio of production or consumption of energy is increasing, but to transform this energy, this fuel in energy, so we need conversion means by we need a conversion means by combustion. This means that we have to use always combustion to transform or to produce energy from this kind of fuels that can be coal, that can be oil, that can be also gas in this area. So we have to use combustion. That is why the combustion will remain the main conversion technology with respect to energy production. And it is why also, if we see here, the percentage of oil and coal, so where we have a two-phase flow, where we can have two-phase, so is very high. That is why we will focus on this multi-phase flow. So that is what we have seen at the beginning. So we have 5 days to go through these topics, and we will start today with more generality issues of multi-phase flow, and then we will try to characterize spray and microprocesses. We sprays as a representative of multi-phase flow. Tomorrow we will continue with the liquid atomization and spray structure, and also try to start with the turbulence and turbulent combustion, because the next day we will focus on the phase change phenomena and the mixture formation, which is related to turbulence and which is subsequent process to liquid atomization and spray structure. Then we will focus on spray transport, interface coupling dynamic. At the end, Thursday, we will focus on turbulence and turbulent combustion, and also then turbulent spray combustion. And at the end, I will give some examples, some application, and also the turbulent dispersed multi-phase combustion at the end, but I have not written it here. So what is multiphase flow? So the multiphase flow is a system with at least two flow phases. One can be called disperse. Here, for example, the particle phase, which consists in liquid or solid, and it can also be gas, and a continuous matrix, which can be also solid, liquid, or gas. It is multi-phase in which we found two phases. We have, for example, liquid solid two-phase, gas solid two-phase, liquid liquid, which is not miscible, and we have here liquid gas two-phase. We can also encounter a three-phase flow. We will see during these courses. Why this is important? So we have economical significance and cost effectivity, because about 70% of all products from chemistry industries are marketed in this dispersed form. It is why this is very important. And at the moment, we have this trend of nanotechnology. And if we look at this production of energy, what we have seen at the beginning of electricity, 4 to 5% of the produced electrical energy is used for mining of particles. This particle can be solid or liquid. So we can characterize these multiphase flows in terms of properties. For example, properties of particles, size distribution of this particle, the form of this particle, the surface of this particle and structures. For example, into particle structures, if we have pores, if the particles are single component or they are multi-component. We can also distinguish them in terms of the particle motion within the flowing Fourier phase or this continuous phase. As we have seen, we have a velocity distribution of particle, for example, and fluctuations. We have also some integral quantities for describing particle fraction in the flowing Fourier phase. We will introduce the phase volume fraction, the mass loading, and we will find naturally these in various application fields. Let me give an example for the properties of particles. Here we have a cold particle. Cold particle has some humidity, and if we bring some heat, so we have a rapid heating, and which come out, it is volatile. They are volatiles, and for that we have these transport processes called devolatilization, and we can also have droplets, liquid droplets, and we will have also due to the heating, so we will have also evaporation. In this case here, we have devolatilization. So there is a building of a layer of volatiles, and we can get to the first combustion of volatiles. And if this is combusting, so these lead to combustion of COX. These also will combust. So we have a very complex phenomena. We have heating, we have devolatilization, combustion of volatiles, combustion of COX, and also we have radiation processes. These can be found in such kind of power generation in which we use coal. This coal should be mined first and bring to combustion in this way. So this was one of a project we have in Germany, so-called transfer project. It is this transfer project 100 29. So this brings me to categorization of flow of systems. So we have seen here now the properties of particles. Now I will see how we can categorize multiphase system due to the particle motion or to the geometry of the system. So if we have these flow conditions, so the interface of the phase and the topology distribution of each phase should be considered if we want to categorize the multiphase flow systems. So we have, for example, at the beginning, a liquid phase. It is flowing in out of laminar flow, and we have a change of thermodynamical properties within, and then we have gas bubble for building, and if we have also some change in the motion, so we can have the liquid droplets, and this kind of system is called so-called transient multiphase system regime. But we can also have what we have almost everywhere. We have a gas phase and the liquid. They are separated by a clear interface, and this interface can be followed, can be captured. And we see here we have large bubbles, and we have also liquid within, and we have here gas phase here, and that is the liquid flow, what we have here. But we can still follow, we can still track this interface, and in this case, we have so-called separated two-phase flow regime. But we have also other regime in which we consider that we have very, very fine, small we have small particles or liquid phase or gas phase. They can also be a liquid phase or solid phase or gas phase and solid phase. They are flowing together. We see here the liquid, so the droplets, or no, the liquid is flowing, and we have a gas bubble within, and the flow, we can consider the liquid phase a Fourier phase and the gas bubble as a dispersed phase. Here, if we have liquid and it's solid. So here, in this case, it is very difficult to track the interface because we have a large number of particles. So it is not really easier to track the interface, and we speak about dispersed phase, and we will focus on this, and we will see clearly how we can characterize this. To sum up, we say that we can characterize the multiphase flow, categorize multiphase system based on the geometry of the flow, if it is laminar, transient, or turbulent. And for in turbulent case, we will introduce also a Reynolds number of particles. We can also categorize them based on the geometry of the interface as we did it here. And based on the turbulent, on the flow characteristic, we will speak about laminar, transient, and turbulent. And we will introduce, as I said, the Reynolds number of particles and some other non-dimensional number to characterize these two-phase flow. Here are some applications. If we have our multi-phase flow in industrial and technical application, we can find this series of constitution of composition. So we have gas-solid flow, for example. We made this in pneumatic conveying, particle separation in cyclone like this one, and filter and fluidized bed. We have also liquid solid, in hydraulic conveying, liquid solid separation, particle dispersion in storage vessel. We have also gas droplet flows in spray drying, spray cooling, as I have shown you before in one example, spray painting, spray scrubber. We have also liquid droplets. If we have mixing of immiscible liquid extraction in the chemical industry, liquid gas flow as we found them in Babel column in some power plants, aeration of sewage water and flotation. But to be very concentrated on one application, we will focus on turbulent spray combustion. And at the end, we will show also some other application related to solid, turbulent solid combustion. So this is one example in aero engine combustion chamber. We have here the liquid fuel it is introduced, and we have here it is compressed in a compressor here, and there is a part of the air which can cool the structure, and one part also is entering the gas chamber, the combustion chamber, excuse me. And here we found this kind of processes. We have atomization and we have also dispersion, and there is a mixture formation, and which can lead to the flame, to the combustion, and the product of this combustion can be, it is always formation of pollutant. We have naturally incomplete combustion, and here we have high temperature which can interact with the turbine blades. So this is what we will focus on, and the question is why we will focus on this. So we will focus on this because we say that the spray combustion is a powerful method of burning relatively involatile liquid fuels. Why we will focus on liquid at the moment, or in the multi-phase on liquid or solid? Because there is a ease of fuel handling, and we can store them very easier. And also they have a high energy content. And all these properties make liquid fuel, solid fuel very attractive for many applications. And in this iron, in this application of generation of energies, this is very, very interesting. And so that we can find this application, for example, in transportation, for transportation purposes, in diesel gasoline engine, heavy engine for road vehicle and ship, and also in aviation, marine and land-based gas turbine, in the space rocket, etc. And what is the fundamental process here? We have liquid at the beginning, and the key process is the disintegration or atomization of this liquid to produce a spray of small droplets to increase the surface area, so that the rate of it and mass transfer during combustion are greatly enhanced. This produce naturally a non-uniformity in composition, and the fuel is present in form of discrete liquid droplets, which may move in different direction with different velocity to that of the main stream of cars. These make also the combustion of this kind of process, of this kind of fuel, different from the combustion of gaseous fuel. And we'll show you here what I said there, because we have to see the energy content of droplets or liquid fuel, or also of solid fuel. It is very high if we compare to these of gases. And we can now say, because the spray formation here is the key process, it play a strong role, or it influences the mixing and consequently the combustion process. So that this combustion process we'll get here is different from what we found in the gases combustion application. So because also this influence is very capital in the spray system, and it is a challenge to optimize the combustion process. And for that, we need also spray simulation tools, which are able to support such kind of development or of optimization. Here, I show you a short example. So we have our burner here. So the spray is spraying, and to build what we have seen before. So the spray with different regions, we will see now with these regions. So, and we have small droplets, they evaporate, and this evaporation build the mixture, and this mixture reaches the stoichiometric condition, so that we have this kind of flame, which is different from naturally what we know like premix flame or diffusion flame. And what is here, that is exactly what I told you before. We have a fuel, we have air which come from the compressor, and here the fuel is entering, and we have the formation of this mixing here within this combustion chamber, and the phenomena which take place are atomization, primary, secondary, we will see dispersion, and we have also some other processes we can find here. And I show there for gas turbine, from the gas turbine, where we can see also the same in the case of IC engines. So as we can see here, so we have also formation of spray, and we have really mixture formation, and we have the spray, and we have a combustion of spray. And the key process is what I say is what I have said before, the liquid atomization and spray propagation. This leads to separation of scales, which is helpful for the description of our process. And it is, we are dealing then with a multi-scale, multiphasic process. As we can see here, this fine diagram proposed by Revillon in 2010. So we have the spray, which is atomized here, and it builds a spray at the beginning. And what is within the spray, we will see that we have a coupling of spray with gas phase. We have also phase space diffusion. We have a PDF formation, so we have evolution of these droplets. We have coalescence and also breakup primary, And secondary, we can also have interaction of the spray with the wall. And then we have the formation, the mixture formation. And during this mixture formation, so we have micro and micro mixing. We have droplet dispersion. We have formation of mixture frac. We can track them by defining some mixture fraction. We have the product of mixing, and we have the turbulent spray combustion at the end. And this combustion has different properties, and also this mixture, we can follow it by describing the liquid mass evolution. We have the evaporation rate. We have also gas fuel topology, and all this is very complex, as we see. And we can also, if we put them in a question, so we have to take into account the dissipation, the mixture fraction fluctuation, the evaporation source terms, and also all these processes. These make what we have to do here very complex. And if we consider the details of the combustion, so we will see that it is normally the combustion regime is very complex. We have also production of soot, of radiation effect. We have also sometimes some flashback processes, and we will see everything here. And I say that we focus on dispersed flow, and I call it now polydispersed because the size of droplets within the system is not the same for all droplets. We have not to deal with monodispersed flow, but with polydispersed flow, as we can see really here, as I showed you at the beginning. So we have also other application of sprays. We can find different application of sprays in industrial furnaces and boilers, in the metallurgical industries, in ceramic and glass industries, and in general manufacturing industries. For example, in metallurgical industries, we can find these in iron and steel industries, in which we have applications such as bio-rating furnaces, direct fire treatment. We found it also in the cement industries, and here we can also find them in the heating of blast furnaces, brick and tunnel kilns, in cement kilns, and we have also here application of drying grain, sand and foodstuff for evaporating brine, paint drying, and so on and so on. I put this application here for references. And which kind of atomizer we use, this will be seen in the next chapter. So, as I told you, we have seen before, we generate through disintegration and the spray atomization different sizes of particles. And different sizes of particles are these different particles of different sizes are flowing within a turbulent flow. And within this turbulent flow, we have also different scales, so that we can have interaction between different scales. And that is what I try to put here together. So we have the size of molecules. It is about in this range of magnitude. So the mean free path length in the order of magnitude. So it is a meter here. And we have the fuel droplets. So they are in this range of magnitude. So millimeter, micrometers. And we have the turbulent length scales. We are here in this range of magnitude. And the flame thickness at the range of millimeter. And we are here And the combustion chamber itself has this range of magnitude. And the power plants are very large, 10 or 100 meter. And we see that we have a very large range of length scales. But if we take a look carefully, we see that the size of droplets and the flame thickness can be almost the same, so that we can get an interaction between that we can have the interaction between droplets in the flame and also interaction with turbulent, which is carrying the droplets. We have also soot formation, and the soot formation can be also influenced by the droplets. And we have normally in such kind of a system, very complex interacting processes and phenomena. And if you want to calculate them, so it is very suitable to use runs, LES or DNS. And we know the advantages of runs and disadvantages of runs. And I think in the other lecture, so Professor Ashoke will tell you about some advantages and disadvantages of runs, LES, and DNS. And we see that if we use runs, so we are able only to catch such kind of the mean values. And here we can try to get the information about the large scales. And here we can get information about all the scales. And this is also related to the computational time we need. So for runs, it can be made very quickly. And for LES, no. And for DNS, we need very, very large time to do this. It is why we will focus. I will show you some DNS results. I will focus on LES and some example of runs. But for that, we need so for that, we need to move now to the next part to characterize our spray and to see what kind of microprocesses take place within such kind of processes. So if I go through these different chapters, so I will say that we will start now with the characterization of sprays and microprocesses. And then I made a slight modification here, and the liquid atomization will follow this one. And after that, we will focus on transport and interface coupling dynamics. And then we'll continue at the end. We'll speak about this kind of turbulent spray combustion. We'll focus on numerical description and description techniques of turbulent dispersed spray, or also solid combustion. And we'll focus on different methodologies, Eulerian Lagrangian. We will also focus on Eulerian. So we'll go through different modeling with these models. And I will also show you how we can use the PDF modeling approaches to describe multiphase processes and also multiphase combustion, multiphase flow combustion. So some remarks. We will have this lecture in 16 hours. And the objectives is that we will try to learn you, especially fundamentals of spray combustion. You will be at the end of this lecture able to identify the role of the interacting multi-scale processes that govern the spray evolution downstream from the near injector atomization region in liquid fueled combustion system. And you will also be able to choose a suitable method for numerical simulating spray propagation, spray evolution, and spray combustion, including also interaction between spray and wall. And you will be aware of the experimental validation issues, because I will speak a little bit about some experiment, about comparison of a numerical result and valid and experimental results. And we'll speak about the modern approaches in the field of turbulent spray combustion or turbulent coal combustion. I am sure that you have the correct prerequisite continual mechanics. So in this continual mechanics, I understand also thermodynamics, some idea about turbulence modeling, but you will get a call by in these lectures by Professor Schocker, and you must have, I think, not deep, but something about combustion. So bibliography, so I use our book. So experiment and numerical simulation of dilute spray turbulent combustions, what we have written in 2011 with Dirk and with Bart Merci. And we use also this book, Multiphase Flow with Droplets and Particles by Shi, Begro, Tuji, and Sommerfeld, and also these these droplets burning in fundamentals of spray combustion from Moshe from US, and also some lecture notes on multiphase flow from myself, from Martin Sommerfeld from Tuji, and also this review we have written in 2018 on primary atomization propulsive devices, fuel injectors. So here I show only how we will speak, what we will speak about. We will speak about the spray atomization, the spray formation, and the mixture formation, and also the result of this mixture formation, and also chemical reaction and combustion. So let me move to the next chapter. I don't know if you have some questions, because it could be better also to interact directly. If there is some questions. If not.
Yeah, so there seems to be no question. Yeah.
Yes.
So, yeah, there seems to be no question. So, Professor Sadiki, you can continue with.
Yes, I see here that there is a question. Can we get the presentation file at the end of the course? So I will send it today, and you will get it today. So the first part, and the next we will get tomorrow at the beginning of the lecture, so that you can follow and perhaps put some comments in the files. Good. So let now focus on characterization of multiphase flow. So we have our configuration here. It is this configuration. So the spray, the liquid is spraying here, and we have a formation of disintegration. We have disintegration process and the involvement of this process here, and we take a small control volume and we zoom it, and we see what is there, and we see that it is a polydispersed system. So we have droplets with different sizes, and we have the gas, and these gas transport or carry these particles, and we'll try now to describe these control volume. So this system here, and this will help us to understand some things or to speak the same language during this lecture. So the first thing is to introduce the volume fraction of particulate phase. I call it particulate phase because this may be solid. This can also be droplets, but in this case here, it is represented by droplets. So we define this as alpha P, and this alpha P I will call it also later on phi or pi. It is the volume of the particle divided by the total volume. So the total volume of particles, it is a volume of each particle multiplied by the number of these particle of this volume, and I sum all and I divide by their total volume. We'll do some exercises in which we can also see it more clearly. So on the other side, we have the volume of fraction, the volume fraction of Carrier phase. It is the volume of the liquid. Sometimes I will put here L to say liquid, but it is the Carrier phase divided by the total volume. And because we don't have empty space here, then we have saturation. So alpha P plus alpha C is equal to 1. But we can also define some quantity related to phases. So we have the so-called phase density. The phase density of the phase density for particle phase, it is the total mass of particle divided by total volume. So we have the density of the particle multiplied by this volume here, divided by the total volume, and this is not nothing else as this here, alpha P. So it is rho P multiplied by the volume fraction of particulate phase. For the Carrier phase, we define it in the same way, and we have rho C multiplied by alpha C. And considering the saturation condition, we have this relationship between rho C B and alpha P. We can also define the density of the mixture, so we can consider that this build a mixture, okay? And if it builds a mixture, so we can define the density of the mixture. It is the sum of these two. So the density of the phase, and in this case, it is only the sum of these 2 parts. We can also define the particle concentration. The particle concentration is the number of particles divided by the total volume. And we define also the mass loading, as I said before. So we say that we can also define some integral quantities, and one of them is this volume fraction of particulate phase, of Carrier phase, and we have also the mass loading. It is normally in gas solid particle laden flow, and it is the mass flow of particle divided by the mass flow of the Carrier phase. And we introduce this expression what we had, and we replace everything by rho P and by alpha. So we have here alpha P multiplied by rho P, and this is this. We can also define it as a mass of particle divided by the mass of the mixture, and we have the ratio of the mass, and here we have the mass loading. If we have this, it is very general what I say there, but we can now specialize it for spherical particles. If all the particles are spherical, then we can replace the volume by its expression for spherical cases. So the volume here is now proportional to the diameter over 3, and we have this expression of alpha p. It is pi, the sum of diameter exponent 3 divided by 6 multiplied by the volume. And the volume concentration now, here we define the particle concentration as this quantity. We can also define the volume concentration. So it is a relative volume ratio. It is can say it is a relative quantity between the volume of particle divided by the volume of liquid of the Fourier phase here, that is fluid. So of the Fourier phase, and it is exactly the ratio of the volume fraction of particle divided by the volume fraction of Fourier phase. We have also the mass concentration. So the mass concentration is the ratio based on these two quantities, because here we have the mass. It is the mass of particle divided by the mass of Fourier phase, and we can transform them and we obtain exactly what we have here. That is this quantity divided by this one. Divided by this one, and we can replace this by 1 minus alpha p. So I told you that we can characterize also two-phase flow based on the regime of the flow. If it is laminar, if it is transient, or if it is turbulent. And for that, we introduce the so-called particle Reynolds number. The particle Reynolds number will be defined in a similar way like the Reynolds number we know in the single phase flow. It is the non-dimensional quantity in which the characteristic length is not the integral length scale or the characteristic length of the flow, but here the characteristic length of the particles, and it is the diameter, because here we deal with the spherical particles, and the velocity is now the relative velocity, and the viscosity is the dynamic viscosity of the flow field. And there is a particular quantity, the so-called particle relaxation time. The particle relaxation time, it is it is a measure of relative importance of particle inertia and fluid acceleration. So it measures the time which the particle need to react with respect to the flow field. And this particular relaxation time, so we will calculate it later, I will show you. We obtain this quantity, it is a sub kind of ratio of the force divided by the velocity. And these readouts, if we have to deal with spherical particle to this quantity, the particular relaxation time, it is proportional to the diameter exponent 2 divided by 18 multiplied by the viscosity, dynamic viscosity, and here we have also the density of the particle. So because we have this quantity which give us a characteristic time of the particles, of the reaction of particle with respect to the flow field, and we know that this particle is flowing within the Fourier phase, we can also derive some characteristic time, some ratio with respect to this characteristic time, the characteristic time of particle out of the flow. And for the flow, we know it is the characteristic length divided by characteristic velocity. And this ratio of particle relaxation time divided by this characteristic time of the flow is defined as the Stokes number. And we see here if the Stokes number is very small, this means that this time is very, very small, so that we can say that the particle follow the flow. And if this Stokes number is very large, this tells us that this time is very large, so that the particle doesn't react with respect to the flow field, and we can say we have no influence of the flow field on the particle. So we will come back to this in a few minutes, and we can also define the collision time. We know if we define the collision time, the time needs two particles to collide, as we have here. So the time between two collisions. If we have the number of density, okay, of particles, we have the relative velocity as we have introduced here in this the relative velocity. And we can consider here a cylinder. And we say that we have our particle with this diameter. And if we have the particle with this diameter, and we suppose that we can get two particles within this tube, and so that we have a diameter of this cylinder for 2D, then we can define the number of particles in this tube. It will be first the surface of this tube multiplied by the length. We have the volume, and we multiply by the relative velocity. The relative velocity multiplied by the time give us this length. And we multiply by the surface, which we have here. And we multiply by the number of density of particles. And as I say, these give out the volume of the tube multiplied by n. And the collision frequency is only the number of particles in the tube divided by this time, so that we have the frequency of the collision, and the time between two collisions will be only the inverse of this time, of this frequency, and we get the collision time as this quantity here. If we have this collision time, then we can also build a ratio between the particle relaxation time and this collision time. If this ratio is very small, what is meant? It means that the collision time is very large with respect to this quantity. This means that the particles are we can say the particles are largely separated, and in this case we can speak about dilute two-phase flow. And if this quantity is large, this means that this collision time is very small, so that we can say that the particles are very close to each other, then the two-phase flow is very dense. And with respect to this, we can then try to make a relationship between, also here it is relationship between the characteristic time. We can also try to make a relationship between the length scales. And for that, we introduce the interparticle spacing. So we say, if we know the real gas theory, so we can say that we have a sphere, an interaction sphere around each particle, and the diameter of this sphere is L. For this one also it is L, and between these two we have the length scale, characteristic length. The interparticle spacing is here L. If we have this, and we say that our particle has a diameter d, then we can define alpha p that as the volume of particle divided by this volume, which is available. This say the total volume. So this is our volume. We had L exponent 3, and then we have this ratio. We introduce this. It is also equal to this quantity. And if we transform a little bit this quantity, we multiply by rho C, and divided by the same quantity here. We multiply also here by rho C, here rho CB, and here rho C, and divided by the same quantity. Then we obtain the concentration Cm, and we have the alpha C, what we have defined before, and also we have this ratio at the end. This means that we can also try to make a ratio between the length scales, this L and this L, as a function of alpha. That is what we will try to do now. So we introduce here alpha C as 1 minus alpha P using this saturation condition. And we now write this expression here. It is this expression what we had, and we put 1 minus alpha P. And this quantity is no other. It is a constant. We put this lambda, and the lambda is this quantity I have put here in blue. And we can say that alpha P is equal to lambda divided by 1 plus lambda. We have two expressions of alpha P, the first one and the second one and the first one, because I would like to get a relationship between the ratio of the length scale as function of mass fraction. Then I put the equality of this quantity and this quantity. And after small transformation, I get the ratio L divided by D is P divided by 6 multiplied by this quantity, and we have this exponent here. And for as example, if we consider gas droplets or gas solid particle flow, we know that in main system we have this ratio almost is equal to 0.001. And if we introduce this quantity here for lambda, and we say that the Cm is equal to 1, then we get an approximation of L to D for this ratio here in this case, and we obtain that L to D is almost 10. This say, I put it here in German, but let me explain. So this say that if this length, so L divided by D is larger than 10 or equal to 10, we can say that there is no interaction between these two particles. We can speak about isolated particle if up from L to D equal to 10. And if we have a volume fraction of this volume fraction alpha P is if it is 1%, by putting this in this relation, in this expression, we'll obtain the spacing. So this L is equal to 3.74 diameter. And if we have this equal to 10, we put only here, and we will get the L equal to 1.74 multiplied by the diameter. So this gives us an idea about the spacing, which spacing, interparticle spacing we can have to obtain isolated particles. They say if where we don't have an interaction between the particles. And putting them together here, we obtain this diagram that is L to D, as we have spoken about now. So we have L to D equal to 10. If it is larger, this means that there is no interaction between the particles. If it is small, we have interaction between particles. And from some other studies, this is our pi, it is now nothing else as our alpha p, so the mass fraction of particle. This corresponds to this value. We can make also a relationship. If we have this quantity here, we have this quantity, we can derive our alpha p, and this alpha p, which corresponds to this quantity, is almost 10 exponent minus 3, as we did here. It corresponds to this quantity here. If we have 100, it corresponds to this one. And in this case, we can now say, if we are in this region, there we have interaction between particles. Here we have particle-particle interactions in this part. In this part here, we don't have interaction between particles. So this part can be called dense two-phase flow region, because we have dense two-phase, we have a large density of particle in a small volume, like we did here. We have to deal with dense two-phase flow regime where the collision time is very, very small, so that these particles come regularly in interaction. So in this area, we don't have turbulent, we don't have interaction between particles. It is the dilute two-phase flow region. And now we can see also these two regions here, first one and the other one. In this region, so we say that we have a two-way coupling. This means that we have interaction between the flow field and the particle field. And in this region, we have one-way coupling. This means that the particles are very dispersed. The distance between particles is very large, so that the particle have no time, the particle doesn't influence the flow field, and we have only one-way coupling, so the particles are carried, they are dispersed by the flow field. But here, because we have the relaxation time, which is also, this is dependent of the volume of a particle diameter. So in this area here, so we have interaction between between the flow field and also the particle phase. So we are here, we have the fluid turbulence, we have the particle. If the fluid turbulence influences the particle, we are here. And if the particle also influences the fluid field, so we have two-way coupling. So we have these two-way coupling. And if we had also the interaction between particle, we have particle, this is 1, 2, we can say 3, 4. Particle, we have 1 and the other one, we have 4-way coupling, 1, 2, 3, 4. So we have 4-way coupling. We have not only the influence of fluid particle on particles, but also the influence of particle on the fluid, and also the influence of particle-particle interactions. So we can have this is a case of gas solid particles. And if I give you this was the mass loading, and with these values here, we will obtain the interparticle spacing of 10 diameter as we did before, and it is exactly this. And for this, we can say that we have isolated particle. In this case, we have influence of particles, and here we don't have influence of interparticle interaction. So how to quantify these couplings? This will be seen in next session. So we will see this now. This is what we will try to quantify here. So we have the fluid phase or the carrier phase. We have the particulate phase or the droplet phase, the particle phase, and there is interaction. Because we have this interaction of phases, and the phases carried some quantities, some physical quantities, and these physical quantities are mass, are momentum, are energy. They can also be entropy. They can also be momentum of momentum. But here I restrict to these three: the mass, the momentum, and energy. Because we have these, the particulate, this particle in the fluid carry this kind of properties, then we have interaction also with respect to mass, momentum, and energy. And if it is in this way, then we can add this this complementary information. So we add here dilute to phase flow, dense to phase flow, one-way coupling, two-way coupling, and four-way coupling. And we have spoken about two-way coupling here. It was not really clear, but what makes it clear is the ratio of this characteristic time, so relaxation time of particle, and the characteristic time of the fluid, the Stokes number. And we have said, if the Stokes number is very high, okay, we have seen that the particles are not influenced by, oh no, the particle does not follow exactly the fluid, the Fourier phase. But if this number here, this ratio is very small, then we have the particle follow the Fourier phase. Why? So this is explained in this diagram. So if the particle, if this quantity is very large, this means that this is proportional to diameter exponent 2. This means that the particles are large with respect to the turbulence length scales here. And if the particles are large, I didn't put a bit here, but we'll see it later on. So if the particles are large, so there is a so-called weight effect behind the particle, and this weight can produce turbulence. And this is why the particle will enhance the prediction of turbulent flow. So this means that the particle influence also the turbulent fluid. And if we have small particles, because this number is smaller than 1, we have small particles, and these small particles with respect to this, to the structure, to the length scales of the turbulence. So we see that this, we can see that this small particle will be tracked, will be tracked by the fluid, and to be moved by the fluid. So there is an exchange of energy. So the fluid must give some energy to these particles so that to get this particle moves and to get this particle trapped by this fluid. And if this fluid gives us part of its energy to the fluid, so the particle and the fluid and the fluid turbulence dissipate, so that we can say the particle enhance dissipation of the turbulence of the Courier phase. We have then this influence, the influence of particle on the fluid phase in dissipating the turbulent flow, and here the particle influence the fluid phase by enhancing the production of turbulent flow. And if it is so, this means that we have also here we have a reduction of the interaction between, we have an augmentation of the interaction of particles, so that this part will enhance the region of particle-particle interaction. That is why we have this corner here to say that in this case, so there is also augmentation of particle-particle interaction. And that is what I will like to show. This come here later, and we can get it here to put this together. So we have one-way coupling. So we have the particle here, it follows the fluid phase. We have the two-way coupling. So the particle influence of the fluid phase, and the fluid phase influence the particle. And we have the four-way coupling. We have additionally the interaction between two particles. And we have also, it was difficult there to classify it. We have here the so-called three-way coupling. This is due to the fact that we have two particles. The first one interact with the fluid phase and modify the fluid phase. This one modify the fluid phase, and we say that this modification implies also modification of this interaction. Then we have a three-way coupling. This influence this, and this influence this. Then we have the three-way coupling. So we have said that we will focus on dispersed two-phase flow. We are here. We have the dilute flow. We have the sparse flow and the dilute flow. And here we have a little bit dense flow. And that is why this part builds the transition between the dispersed flow and the dense flow, in which we have two kinds of flows. We have here the collision-dominated flow, that is like we get in some mountains, or we have also contact-dominated flow in a granular flow, for example. That is a very nice presentation in this book of multiphase flow in 2004. So let me now come back to the quantification of these two-phase flows, of these effects. To quantify these effects here, we have to introduce some properties, and these properties will be given by so-called the dynamic relaxation time, as I introduced it before, and we will have the possibility to define it correctly. And by defining it, we will then come back to the ratio of the characteristic time. So we consider that the particle to be moved need forces. So applied force on the particle, the first one is the drag force. The other forces will be seen later on when we will try to characterize the motion in a general way of a particle within the Courier phase. Let us consider only the drag force. This is the drag coefficient. In the volume here, we have a mass multiplied by this quantity, and we have the relative velocity. I will show you how we got this relation in a very nice way. So at the moment, we can only believe on this. So we get this expression. We have a coefficient here. We have a parameter. We have the drag coefficient. We have the relation, the relative velocity, particle velocity, and fluid velocity. and we assume that our particles are solid particles, and we can put them in this expression. So if we put the mass there, we replace this here by this quantity, and we obtain exactly what we have here. And this is really what we have. We have the surface. The surface make the surface of the particle, which is impacted by the flow field of the Fourier phase. It is this one here. And we have these drag coefficient I put now here with D. I could put also D, it is in Germany, yeah? So Widerstand, but it is this quantity. So we have our particle, so the flow is coming here, that is the surface, which is orthogonal to the velocity, to the direction of the fluid flow. And this is the surface. And here, if we see now clearly, we see that we have this quantity, and this quantity is now is exactly what we had before. As we have before, it is our relaxation time. And we can also see it if we relate it again to the diameter, to the relative velocity, to the particle Reynolds number, as we introduced it before. We introduced this here by replacing these velocities here by this quantity. Then we obtain now this relationship. And if we put this quantity here, this divided by this here, we call it a quantity F. And this quantity F will give us we will go into details on this quantity as when we will speak about really the complete interaction of fluid phase and particulate phase. We call this quantity F, and then we get this quantity here, what we had before, that is the relaxation time, okay? I think you remember this quantity as we introduced it before. It is this quantity, what we had, the relaxation time, okay? And the other one is related with the ratio. We have 3D here. If we put as a function of the diameter, it is exactly what we had there. It is the inverse of the relaxation time. And if now we say that we have the so-called Stokes number, this means where we have this quantity equal to 1. Okay, this means that we don't have a turbulent flow, we have laminar flow within this two-phase system, and we get these quantities approximately equal to 1. This means that the drag coefficient is equal to 24 divided by the particular Reynolds number. We will see it also later on, but here I put it at this point. And now if it is equal to 1, so we have the so-called Stokes flow. We have 1. And if we now try to solve this equation, so we put dt here, and we consider that the velocity of the particle of the flow field is constant, and we say at the beginning we have the particle, we have the velocity of the particle is equal to 0 at the beginning time, and as a condition for this solution, then we obtain that the velocity of the particle is proportional to the velocity of the fluid flow multiplied by this quantity here. Okay. So the time needed by the particle to change its velocity from this value at the beginning to this value here let me say, to change its velocity from this quantity to 63.2% of the fluid flow, this time is called particle relaxation time. And why this value? So this value is given by the, if we go in the rheology, we will find also the so-called relaxation time. It is the time which our system need to change its properties here, the velocity from 0 to this percentage of the volume of the velocity of the fluid flow. So we say that if we have this time equal to this one, we have exponent here equal to 1, okay? Then this quantity will correspond exactly to this percentage. The time need by your particle to have the velocity to change its velocity from this quantity to the quantity corresponding to this time equal to tau p, and this quantity will be this one of the velocity of the flow. So here I put t equal to tau p, and I calculate it, and we obtain this quantity multiplied by 4. This means that the relaxation time is the time taken by the particle to change its velocity from this quantity to this value of the velocity of the fluid. And this is what we had before. It is the time needed by the particle to react to the flow field problem, to the flow field motion. And as I said, it is a measure of relative importance of particle inertia and fluid acceleration. So if we have this, we see exactly what we have here. So the time, we have this ratio. So this ratio here give us this quantity, okay? And we have, if the time t equal to tau p, here tau p, I put v to say that it is the velocity momentum interaction, and these correspond exactly to this value here, and it is 63%. And this means that the relaxation time, the time need by the particle to get this value here of the volume of the fluid particle. So, and we can directly derive what we have spoken about before. For water droplet in standard air diameter 100 micrometer, and it needs a relaxation time here of 30 milliseconds. And we see here, if the Stokes number, it is Stokes number related to the momentum. That is why I changed the indices here. So the particle and fluid flow will be near equilibrium, and the particle will follow the flow. And if the Stokes number is larger, the particle will be unaffected by the fluid flow, as we see here from this tracking the particle trajectory. If we consider free shear layer, and where we have a larger scale vortex, we have particle and flow field. So we have here the particle for small Stokes number will follow the flow, and for large the Stokes number, it will not follow the flow. Here we have the interaction between both, and this explain, which we can counter later on, the interaction between particle and eddies, and also this allow us to explain the heterogeneity in particle concentration field based on the preferential concentrations. So if we have this, we can also introduce another kind of interaction. This is interaction based on momentum. And let me now focus on this interaction based on if we have phase change, for example, particle evaporation. And I think it is perhaps time. I don't know if it is, let me know if I can continue or it is time to close this session.
You can continue for another 10 minutes and then take up the question and answer and things like that.
Okay.
I mean, if it is okay with you, I mean, in fact, we can go a little beyond that. I mean, that's not a problem. So 10-15 minutes, you can go ahead and then,
Okay.
yeah.
We have 3 slides to go through, and it can take 10 or 15 minutes. So if we have phase change like evaporation process, what occur there? So we have a particle, we have the heat, which is flowing, which is providing to the particle. And we see that the temperature of the particle will change. And we have a liquid phase. The particle the heating process will take place within the particle, and some quantity of species will go out. We have the evaporation rate, and here we have some species which will be evaporated from the liquid phase. So if we have this, what is the process? We have first the heat transfer process, and we have also the heat conduction process. So the continuous phase, in the continuous phase, we have the Fourier law, in which we have the thermal conductivity, we have the gradient of the temperature, and we can write this Fourier law for heat conduction. For heat transfer, because here we have the interface, okay, we have the heat transfer will be equal to the relative, to the difference of the temperature. This is the temperature of the Carrier phase, and this is the temperature of the particle, because we have the interface, we have some kind of discontinuity, and we have a temperature jump, and we have the proportionality coefficient, it is the heat transfer coefficient. Now we have to deal with 2 quantities. We make the ratio of both. We have the heat transfer coefficient divided by this. We divide this quantity divided by this one, and we have 1 divided by meter. This meter is come from this ratio here. We have the difference of the temperature divided by the space, and this space is this meter, and the difference of temperature is TC minus TD. So then we have the relationship between the heat transfer coefficient and the thermal conductivity. We have then this quantity is proportional to this quantity here divided by meter, and this meter is only there. It is a length scale. The proportionality coefficient, the Nusselt's number, so it is a measure of the quantity of heat which is transferred to the other phase. And we can see later on, or we will deduce that the Nusselt's number is a function of Reynolds number and the Prandtl number. So if we deal with the mass fraction, so because here we had not only the change in the temperature, but also we have a change in the mass, in the species of the evaporation rate we had there. Then we have a change in the mass, and we have then the mass transfer. So the mass transfer here is given by a similar expression. The mass change per unit of time is equal to the mass transfer coefficient multiplied by this difference of the mass fraction in the area where we have no change of this quantity here very far from the interface, and minus the mass fraction on the interface. And this is this here. And we have also the diffusion process. We can also have this change due to the diffusion coefficient. And this is exactly like this. It is the Fourier law. And here we have also the ratio of the gradient of this quantity, the mass fraction, along the, wait, it is here, I didn't put it. I will come back to this. If we have our particle and we have the mass which is going through the interface, and we follow the normal, the unity vector to this interface, and it is this one. We have a gradient along this direction due to the diffusion of species. Now we can make the same ratio. We can build the same ratio here. We have this quantity here divided by this one, okay? And this, I put this diffusion, but it is this quantity here. And we get exactly the same relationship, 1 divided by the length here, so that we can write this quantity, yeah? Now I write it correctly. It is this quantity multiplied by this diffusion coefficient divided by the length, characteristic length, and the proportionality coefficient is so-called the Sherwood number. It is the mass of the diffusion of the mass transfer across this interface. We will also show that this Sherwood number is a function of Reynolds number and Schmidt number, and the Schmidt number is only the ratio of viscous diffusion rate and molecular diffusion rate. The Prandtl number is related to the temperature. Then, having this, let me now put them again together. I will now like to replace this quantity here and this quantity there. By putting them, I obtain this expression, okay, of the Nusselt's number, and we multiply by the interface. That is this quantity on both parts, this part and this part. Then we have the heat transfer per unit time. And I put this now. So it is exactly what we have. It is the capacity coefficient multiplied by the temperature. And it is for the particle divided by time. And it is nothing like this multiplied by S. It is what we had. And this means that this quantity, what we have here, give us a relationship between the change of the temperature of the particle as function of the difference of the part of the temperature between the Fourier phase and the droplets as function also of the Nusselt's number. We will see also the same if we can also compare, let me come back to this. We can compare this expression with what we had before for the change based on the dynamic relaxation time. We have the drag force, and we had also the relation, the difference of the velocity here, and we had here the drag coefficient, and we have here the change of the momentum of the particles. Here we have now the change of the temperature of the particles. We have all the change of this quantity. We have these replaced with our drag coefficient, and we have the difference now of the temperature. For mass, we will get almost the same. And if now I replace the diameter we had here, divided by, as we replace it by our mass by this quantity, and we introduce a quantity. So we do exactly what we did there, and we replace this quantity, what we will obtain here, by the relaxation time with respect to the thermal interaction. So let me say now we put this quantity here, we get what we have here. And this quantity here is nothing else like this. We compare this with what we obtained before the dynamic relaxation time, and it is exactly this. And we have this factor here, it was our F divided by relaxation time. We have now this quantity. This quantity can be called F, but for the thermal interaction, and if it is equal to 1, we have also the Stokes number, Stokes flow, where the particle Reynolds number is low. We have to deal with almost laminar flows. And in this case, we have 1 divided by this quantity. Now this is the inverse of this one. And we obtain also the expression of the temperature of particle and the difference of the particles here. I put here for fluid, for TC, and here for particle, and it is this one. We can solve also this equation by considering that we have a constant temperature of the fluid, and the particle change is by the temperature in interaction while interacting with the fluid flow from the starting temperature of 0 to this end temperature, which is here. And then we can define also this relaxation time, the thermal relaxation time. If T equal to this quantity, then we get exactly the same relationship as we got. We have this quantity. This means that the time needed by our particle to change its temperature from this quantity here, what we have there, to this value correspond to what we call the thermal relaxation time. And the question will be now, what is the relationship between the the thermal relaxation time and the dynamic relaxation time or relaxation time of particle? We build these two, the ratio of this quantity and this one, and we obtain that it is a small calculation. We will obtain that it is proportional to 1 divided by the Prandtl number. And the Prandtl number, it is exactly the same like we did for the Stokes number, but here we deal now not with the viscosity, but here with the capacity, calorific, the thermal conductivity and the specific heat. And we got this ratio, and we can say for gas, so the Prandtl number is almost equal to 1, then this ratio is almost the same. But for liquid, so the Prandtl number is high, and we see that this ratio is very small. We can say that the gas response time are the same order of the magnitude, but for liquid, the velocity equilibrium is achieved much more rapidly than the thermal equilibrium. So we have these two kinds of relaxation time, the dynamic relaxation time and the thermal relaxation time. These two quantities will help us to quantify correctly this coupling, the mass coupling, the momentum coupling, and the energy coupling. So let's suppose, I think you will stop me if it is needed. I continue.
Yeah, you can, I mean, wherever you can bring it to something, then we can take up the questions answer session.
Yes, I think here it is a very good location to stop.
Okay, okay, thanks. Yeah, so I mean, the participants can type their questions in the chat box, and let's say, yeah, there are some questions. You can also see those questions. Can you see those, Professor Sadiki? I mean,
Yeah, I have now.
yeah, that if you are that Q&A, if you click,
Yes.
yeah,
Yes.
I think the first one I see that length scale.
I see the first one from Ashutosh.
Yeah, yes, correct.
Which length scale is L? As we know, there is a range in complex flow. Oh, the L I introduced here. So let's come back first to the. I don't understand which you are speaking about, which L, because we have this is one. This L is a length scale, a clear length scale of the system, but the L we have introduced before, it is the interparticle spacing. It is this L here, okay, and this diameter. But what we introduce here, it is only a length scale of the system. So because we have here the gradient of the temperature, this means that delta T divided by delta X, and this X, it is a length, and this is what we have here. I don't know if it is clear for our.
Yeah, Ashutosh, I can allow you to talk, so you can talk.
Yeah.
You can unmute yourself and talk.
Yeah, hello.
Yeah.
Yeah, good afternoon, sir. Thank you
Yeah,
for having me.
yeah, just
Uh,
1 second. If any other participant would like to, you may raise your hand, then I can allow you to talk. I think that way we can avoid other disturbances and things like that.
Yeah.
Yeah, go ahead.
Yeah,
Ashutosh.
Professor, can you hear me? Like,
Yeah,
Yes,
you're audible.
yes, I follow you.
in the initial slides during the calculation of the Stokes number, if you can move to that slide. The first few slides when we introduced the relaxation time. Yeah,
Yeah.
in this slide,
Yeah.
for the calculation of the time scale of the flow, we have used L.
Yeah, this L is.
Yeah, so there are a number of, length scales are there, smaller scales are there, and also larger scales are there. So my question is, which scale we are using here actually?
This one, it is the integral length scale.
Okay, thank you. Actually, that was the question. Yeah.
Okay, but you had another question.
So the other question is like when we are considering the static particle, like zero velocity particles are introduced in the flow, then okay, Stokes number will predict whether they will follow the flow or not. But if the particle had some initial velocity that is perpendicular to the flow, then how this concept will be applied, like particle flow followability? That is my question.
No, it depends only on the diameter of the particle.
Okay, this will not depend on the flow velocity of the droplet.
No,
If
it
the
depends
droplet-
really on the ratio of the relaxation time. So we have the relaxation time divided by the fluid relaxation time. If it is large, as we had here, yeah, if it is if this Stokes number is large, then it doesn't follow the flow. Yeah, if yes, it will follow the flow. Okay, if it is very small. So now it depends on which kind of how to express this following the flow. If we have two different velocity, like in jet in cross flow,
Yeah, exactly.
we see that anyway, the particle will follow the flow if we follow really the evolution or the trajectory of the particles. At the beginning, it is not really so, but after that, it will follow the flow.
Okay, thank you.
Okay, thank you, Ashutosh. So, so your all the queries are taken care of, right? Ashutosh?
Yeah, yes, yeah.
Okay,
absolutely.
thanks.
Thank you.
Yeah, so Neha, I would allow you to talk, so you can also unmute yourself and then pose your question.
Hi, good afternoon, sir.
Yeah.
My question is for the same slide. The question is that here in the Reynolds number calculation, you've mentioned the dynamic viscosity. So I wanted to ask that if it would be a liquid and gaseous flow phase, which dynamic viscosity do we need to consider here for these calculations, for liquid or for
Can
gaseous?
you speak louder?
Yeah, I may read out his question is there in that. I think her question is, in case of liquid gas flow for Reynolds number calculation, now when you go to dynamic viscosity or dynamic viscosity of which phase would be used? Is it liquid or gas?
No, the Courier phase. Viscosity.
So it is gas.
Yeah, and it is it is gas in this case. For example, we have droplets and gas. So the gas is the Courier phase, so you will take the dynamic viscosity of gas.
Okay, thank you.
Yeah, any other questions or anything? If you may raise your hand, I can allow you to unmute and talk. Okay, so yeah, I mean, yeah, there is one small change. Yeah, Professor Sadiq, if you stop sharing, then I'll share that and we'll show these people. Yeah, you may stop sharing, then I can share.
Yeah, only the question is, we will start
In another 2 hours time.
in 2 hours.
Yeah.
Okay. Okay, they are.
Yeah, no, it's still your slides are visible. So if you can stop sharing.
Okay.
You just need to stop. Yeah, fantastic. So, yeah.
And perhaps
yeah, I wanted to show them this small change which you showed. Yeah, every day our sessions is at in 3:05 and 7 to 9. So these are the sessions. These are there in the website also. So I think there is some confusion there. So, and then second, there is a one shuffling in the lecture. So tomorrow, one session, today, other session also would be taken by Professor Sadiki. Then tomorrow, first 1 hour he will take. Then
now I change this if I can say something.
Yeah.
So put this lecture here on the lecture 2 today,
Yeah.
and one will be moved here.
So what do we move?
Lecture 2.4
Mhm.
is tomorrow.
Okay,
Lecture 5,
we move
is-
it here.
yes.
Okay, so that's fine. So
We started with it today. I will continue after the break.
no, but tomorrow, yeah, so tomorrow we have 3 hours of turbulence session. So,
Yes.
so today you have this. So, okay. So yeah, I mean, that you can do. I mean, the idea is that tomorrow I would take 3 hours, then follow up day morning, I will finish.
Yes.
I will wind it up, then you will continue with everything has been kind of pushed down, nothing else.
Yes.
Yeah, I mean, in between you can, I mean, do that suppling. That's not a problem.
Yes. So tomorrow we take 1 hour.
Yeah, then I will take it up. Rest I will take it up. So you may not need to, I mean, come back.
Yes.
Okay. Then day after tomorrow, I mean, 7th, first 1 hour I'll take, and then I will hand it over to you.
Yes.
Okay.
And perhaps to Ashutosh again for his question. If you see also result of some crossing flow, jetting cross flow, liquid jetting cross flow, you see exactly that the droplets follow the flow. But with with a modified trajectory, so either you had a perpendicular velocity, and after that the velocity, the trajectory is curved and trying to follow the fluid, the Courier phase.
So thank you very much. So we'll kind of join back again. Same link would work in a couple of hours time. Okay. Thank you.